My name's Dan Jansen again. But I should mention my co-author on this is Brett Schaap. He is a graduate student of mine. He now works for Mark Thomas up in Sacramento. And so I've got the privilege of discussing this, a part of his work. This is just a fraction of it. There's some things I'll skip over, but if you've got questions, I might be able to remember the content of the rest of it. The objectives of this portion of the work, it sort of stemmed from this idea that if you use recycled concrete aggregates, it increases the drying shrinkage of the concrete. Okay, it's accepted, we've seen it, but then it sort of begged the question, why are we seeing more drying shrinkage when we use recycled concrete aggregate? The simple answer is there's some adhered mortar to the recycled concrete aggregate, and the thought is that that continues to shrink. But, you know, in thinking about this, it's that concrete might be 10, 20, 30 years old. It's already gone through a lot of drying. In concrete, even after you re-wet it, it doesn't completely swell, and then when you dry it, it doesn't shrink as much. So it sort of begged the question, well, why are we really seeing that much drying shrinkage? And is there something more than just this adhered mortar continues to exhibit some additional shrinkage? So that was sort of one of the underlying objectives of Brett's research, and there was a couple other things, but that's sort of the focus of what I'm presenting here, and that really is to gain some kind of insight as to how much the paste phase of the recycled concrete aggregate contributes to the overall shrinkage of the concrete, and I really should say the mortar phase, because that's what I'm emphasizing here. The outline, I'm going to give it a little description of the aggregates and the concrete batches that we made. I won't completely talk about all the concrete batches, it just gets into too much detail. It'll talk about the determination of the modulus of elasticity of aggregates, because that does have some input to the final analysis. And then I'll talk about the shrinkage testing, results and analysis, and then how we modeled it to try to draw some conclusions, and which means I'll end up with some conclusions. So the coarse aggregates, as our reference, we've got a local granite aggregate. In terms of shape, it was most similar to recycled concrete aggregates. It's a crushed granite. It's one that we've got experience with in our area. It's an okay aggregate. We're in San Luis Obispo. We don't have the greatest aggregates in our area, but it is what it is. And you got to sometimes work with what you got. The recycled aggregates we're using, we actually had two different types. One was an aggregate that was recycled in San Diego, and then shipped up to us. They sent us 2 tons of recycled aggregates. I still have some in the lab. But anyways, it turns out to be a pretty high quality recycled aggregate. I think the parent aggregate was actually very, very high quality. And so we'll see some of that come out in the results. And then the other thing we did is we made our own recycled aggregate. And that way we understood, we're hoping to have better understanding of what the properties of the recycled concrete was. And so we made our own, and when we made it, we went and used our original granite, so it had sort of the same properties. And so as you can see, we've got, you know, there's some parent aggregate and then some adhered mortar, and I will describe the rest of those aggregates here. So here's all the description of the different aggregates we used. We had a local sand. This is the crushed granite that I'm talking about. I'll refer to that as N, normal, natural, whatever you want to call it, but that's our type N. Typical specific gravity 2.61, 1.4% absorption. And then here's our recycled concrete aggregate. This is one that came from San Diego. Like I said, it was a good high quality one, lower specific gravity, but that's pretty typical as well. And pretty high absorption, again, pretty typical for recycled concrete. And then here's 4 of them that we manufactured. And we manufactured them and handled them in different ways with the intention of trying to gain some insight to this. So first of all, we had our manufactured one, and when we manufactured it, we made it with water cement ratio 0.45, with the same as this natural coarse aggregate, but we kept it in a saturated state. We never let it dry at all. And that way it's never gone through any drying shrinkage. And so we kept it wet. When we crushed it, it was moist. We kept it moist, and then when we put it in the concrete, it had never gone through any drying. So we had that aggregate, and then we had another one, exactly the same, except that after we crushed it, we let it dry out. And so it went through all the drying. Before we made concrete with it, we did saturate it again and worked with a moist aggregate. And then we had two others. We manufactured another one where we did let it dry out as well, but with a water cement ratio of 0.3 and another with 0.6. I probably won't talk about these too much, but these two also went through drying before we actually used them, which is what our aggregates would normally see. The most interesting results actually came out of the comparison between these two, but then there's also some issues that came along with it. Pretty typical, all of these ended up with about the same specific gravity, all had about the same amount of absorption. I'm pulling this off the top of my head, but the RCA had a mortar content of 34%. So we actually measured that, and one of the failures here is that we failed to measure what the adhered mortar of the actual manufactured aggregates are. The original thought was that we could just go to the mix design and figure out how much mortar there is in it, except that during the process and crushing, you lose a lot of the mortar. It was sieved over number 4 sieve, and so a lot of the mortar phase was lost. So we actually don't know what the adhered mortar content of these the ones we manufactured ourselves. So unfortunately, that does hinder some of the analysis. The gradations, sort of similar. They're all satisfying a size 5/7, which is, I think, a 1 inch by number 4 coarse aggregate. The natural aggregate that we have from our local quarry does not have very much below the 10 millimeters, or let's see, that'd be a 3/8 inch 3/8 inch sieve. The crushed stuff does have more. We did sieve the ones we manufactured over number 4 sieve, so everything had a pretty low passing content passing in number 4 sieve. And so here's the batches of concrete that we produced with all this. And so we did manufacture concrete using all these recycled materials with water cement ratios of 0.3, 0.45, and 0.6. With our natural aggregate, we made one batch with each of those, and then we actually made 2 batches with the water cement ratio of 0.45. And then with this recycled aggregate, one batch 100% replacement of the coarse aggregate with the recycled San Diego material, and then 25, 50, 75%, and 100% replacement. Those are replacements by volume. And then up at 0.6 as well. The one that we saturated and the one that we dried before using it, we manufactured concretes with the water cement ratio of 0.3, 0.45 at 50% replacement and 100% replacement, and then 0.6. And then here's the ones that the recycled concrete had lower and higher water cement ratios. Very limited part of this study. All total, there was 20 mixes that we ended up analyzing in this. So the first part of this is talking about the modulus elasticity, because it does have a big impact on this. So we just did static modulus. We did some dynamic modulus, but that's another part of the study, and we looked at modulus elasticity over time and how the strength of mortar changed. But the big part is the modulus elasticity. There was a really noticeable difference. And particularly these 3 here, these are the 3 aggregates that we made that we allowed to dry out before we used, and they ended up showing with much lower modulus elasticity. Coincidentally, the compressive strengths were also a lot lower with those 3. A little bit of question, and I've got a few conclusions, but I'm not quite sure why that ended up occurring. But the concrete with the aggregate, the recycled aggregate from San Diego, actually had equivalent or better modulus elasticities than even our natural aggregate, which is sort of surprising. But like I said, the parent aggregate that was used in that was actually really high quality. It's really high quality recycled concrete, as good as the virgin aggregate that we have from San Luis Obispo. And then the one where we manufactured water cement ratio 0.45 and it was allowed to stay in the saturated state, provided pretty comparable modulus elasticities over the different water cement ratios. So we did a fairly complicated analysis. Actually, I shouldn't say it was that complicated. It was actually pretty simple. I used the exponential mixture rules. This looks long, looks complicated, but it's actually a fairly simple equation. It's basically saying that the predicted modulus elasticity is a function of the modulus elasticity of each component to the power of its volume fraction. So if you don't have one of those components in it, the volume fraction is 0, and some constant to the power of 0 is just 1, so those terms just, a lot of them disappear. So as an example, our batch, which is R4525, that means it's using the recycled aggregate, the one from San Diego. The water cement ratio of the concrete is 0.45, and we're doing a 25% replacement of the coarse aggregate with that. And so we've got the natural coarse aggregate. This is the volume fraction of the total volume of the concrete that's occupied by it. Here's the modulus elasticity of the recycled aggregate. This is its volume fraction. And then I just looked at the mortar phase. So all these mortar phases were all the same instead of trying to separate cement paste from the fine aggregates, which I wasn't able to do. But all total, the mortar was occupying 63% of the total volume fraction of the concrete. That means these two together are 37% is the coarse aggregates. So use least squares regression. We had 20 batches and 9 unknowns, which are all the different modulus elasticities. 20 batches, did a least squares regression, and we can back calculate what the modulus elasticities of all these aggregates are. And so, quick comparison. Here's the measured static modulus elasticity, I should say the modulus elasticity of the concrete, and using that regression model, here's our prediction, and pretty good fit. So I'm pretty comfortable that this predicts the modulus elasticities of the aggregates, so we're back calculating those pretty accurately. And so here's the results of what we got. Starting off with the mortar phases, the mortar phase, the one that we had with the water cement ratio 0.3, about 28 gigapascal, and then with the water cement ratio 0.45, it was about 23 gigapascal, and with the water cement ratio 0.6, 18.5. Trend makes total sense. The higher the water cement ratio, the lower the modulus elasticity, so that makes complete sense. Over with these three aggregates, they all came out pretty similar. And so here's our natural aggregate, about 38 gigapascal, a little bit higher than our mortars, or actually considerably higher than our mortar phases. So that makes sense. The recycled aggregate, the one from San Diego, actually had a higher modulus elasticity, and that's what I was saying. It was a really high quality one. We've experienced this over and over again. It actually produces higher strength than concrete with our local materials. But then here's the one where we manufacture our own aggregate and left it saturated. Little decrease in the modulus elasticity, but not a whole lot. Now, the ones that had dried out, this is where it starts getting a little fuzzy. This aggregate, or these two should have been identical or very similar, but something went on with this drying, and we just did not see the increase in strength and increase in modulus elasticity. And so we did end up with much lower modulus elasticities. So that's our modulus elasticity. So we got the models, we got the values for the modulus elasticities of our different components, and so it's on to the drying shrinkage. We moist cured them and then took them out, and then did drying shrinkage at 50% relative humidity, 23 degrees centigrade, measured them over time, and this is sort of what we got. Typical curves. And so this is the one where we had water cement ratio 0.3, 100% replacement of all the aggregates. And up at the very, very top, the largest, actually let me start off with the natural aggregate, sort of our reference. was actually sort of falling in the middle. The one with the aggregate from San Diego that was recycled has a very similar pattern, very similar path. The aggregates seem pretty similar, although the recycled one has this extra adhered mortar. Not a whole lot of extra drying shrinkage. But the one where it was made with the lower water cement ratio did have a lower amount of drying shrinkage. This one was allowed to dry out before we worked with it, and then, sorry, I take that back. This was the one where we kept the aggregate saturated the entire time. And so that was a little bit of, so we kept it saturated, so we actually would have expected this one to have greater amount of drying shrinkage. We didn't see that, which this is where it's one of the things that's a little surprising here. And then the one where we allowed the aggregate to dry out more, or allowed to dry out and went through drying shrinkage before we used it, we ended up seeing a much larger amount of drying shrinkage. Those two seem flip-flopped. I mean, every time I looked at it, it's like, are you sure you didn't get these two sets of data mixed up? Which wasn't actually the case. And there is actually an explanation for why this one ended up shrinking so much more. With the water cement ratio 0.45, we had a lot more batches to it, and so it just gets a little more cloudy here. But a couple of important ones. So at this point, we actually made 2 batches with our natural aggregate with the water cement ratio 0.45. Those two came out, a little bit of difference, and sort of shows you just the natural variation. You make 2 batches, you're going to get some differences, and so that's about the level of expectation. But those two did come out with the lowest amount of drying shrinkage, and then the one with the recycled aggregate from San Diego, that's this orange one. It did have a little bit higher drying shrinkage. Again, that's sort of where we're expecting it to go. And then the one where it was saturated, it wasn't really actually the highest. So the 3 highest were actually these 3 right in here, which again wasn't really quite what we're anticipating. So, and then again with the water cement ratio of 0.6, again we're sort of seeing that same trend. The natural aggregate, this is the recycled aggregate from San Diego, and this is actually one that's making a little more sense. The one that was saturated does have the largest amount of drying shrinkage, and then the one that our manufactured aggregate that was allowed to dry out first had a little bit lower shrinkage. We looked at 2 different ultimate shrinkage models. One is from ACI 209, the other is from RILAM TC 107. 2 different shrinkage models. In effect, they're sort of the same. I kept the original terminology just so we don't get these 2 mixed up, but this is the shrinkage at some time t. This is the shrinkage at some time t. There's an ultimate shrinkage term. ACI 209 uses S alt, and then RILAM TC 107 has this epsilon SH at time infinity. In theory, these 2 should be the same values, except RILAM has this 1 minus relative humidity to the cube power term, and if we use the relative humidity 50%, which is what we're using, then this 1 minus h cubed term becomes 0.875, which actually tells us that S alt should be about 0.875 of the ultimate shrinkage strain. And so here's our test results. We model all those curves just so we can get one number to do these ultimate shrinkage comparisons with. These are the 20 batches that we made, and here's the S alt and epsilon SH in infinity terms. And if we take S alt over epsilon SH infinity, divide them, those terms should be 0.875. So regardless, these models are about the same, so it doesn't really matter which term we end up using. And when we average them out, we get 0.858. And I think if we get rid of this one low-lying term, this comes out right on 0.875. So happy with that. And so, like I said, S alt should be 0.875. For the rest of the analysis, I'm just going with this S alt as the term that I'm analyzing. Didn't really matter which one I went with. These 3 batches I'm not going to talk about too much because the modeling I'm going to work with is a 2-phase model, and these because they're partial replacements of the coarse aggregate, it ends up requiring a three-phase model, and so I'm not actually going to talk about or include those in the rest of the analysis. And so the shrinkage model, I picked a really simple one because I'm trying to understand the process here. So I took a relatively simple model. Whoops, wrong button. There we go. So I'm taking a relatively simple model. It's been used by others. If Will Jansen is here, no, I don't see him in the audience. I pulled it off of one of his papers, where the shrinkage is related to the amount of shrinkage of the paste, the volume fraction of the aggregates, and the relative modulus elasticity of the paste and the concrete. I'm working with the mortar fraction, and so I replace the paste with the mortar, and the volume of the aggregate, again, that's still the volume fraction of the aggregate, and this is the shrinkage of the mortar. Rearranging this term, so I can calculate, with S-alt, I can calculate the shrinkage of the mortar. So I look at these two mixes. These are actually identical mixes. I've got the modulus elasticity of the concrete. I've got the modulus elasticity of the aggregate. I've got the modulus elasticity of the mortar. That was from the previous phase, which is why I talked about that. We measured what this ultimate shrinkage strain is, and so we can back calculate what the shrinkage of the mortar is. Two different batches, we're getting something pretty similar. So again, I'm reasonably happy with this. We're taking an average right here of the shrinkage of the mortar with the water cement ratio of 0.45 and 1297. And so that's going to be my reference value. And so I can now use that, going back to this equation. So I'm going back to this equation. So I'm going to use those values for example, this is what the recycled aggregate from San Diego. We know what the modulus elasticity of the concrete is. We know what the modulus elasticity of the aggregate is, the modulus elasticity of the mortar. We measured what the ultimate shrinkage strain is, and then we've got the modulus elasticity of the mortar, which we just calculated, and we can now predict what this should be. And the idea is that if in theory, we should exactly match this value here. If the prediction comes out higher, that means the aggregate is somehow contributing extra shrinkage, and it's not just the rigidity of the aggregate that's reducing or increasing the amount of shrinkage. And so when we do this, the prediction that we end up getting is that S-alt comes out to be 649 times 10 to the minus 6 strains. And so we ended up seeing a lot larger shrinkage than what we'd really expect. And so again, this prediction is including how stiff that aggregate is, which should inhibit the shrinkage of that newly fresh placed mortar around it. And what we're seeing is that we've got a 31% increase in drying shrinkage. So that adhered mortar phase is actually really contributing quite significantly to the amount of drying shrinkage of the concrete. Even though with this batch, we actually didn't see too much of a change, but we are getting, well, I was going to say we didn't see too much change. We did see some additional increase here. Now, it really plays a bigger role when the modulus elasticity of the aggregates change, whether they're a lot larger or end up being a lot smaller. And so looking at that for running through the same analysis with the rest of the batches with that had the water cement ratio 0.45. This is where we're predicting the shrinkages should be. This is what we actually measured the ultimate shrinkages to be, and this is that ratio. So again, if this ratio ends up being a lot larger than what it was supposed to be, then like this one here, 31% larger, that means the aggregate is making it shrink a lot more. And so we're seeing, a lot of extra shrinkage here with this one, 25%. Well, that was the one that was saturated the entire time. This is our aggregate that we made the entire time. It was saturated. We see considerably larger drying shrinkage than we would expect. And when we made it with the same aggregate, but we allowed it to dry beforehand, we don't get as much additional drying shrinkage. Again, it's making sense, but we're getting a little quantification here. And then What's a little more surprising is when this is the aggregate that we made that was a little higher strength. It was allowed to dry out ahead of time. Didn't actually really add any additional shrinkage by itself. Even though this measured ultimate shrinkage is a lot larger, this extra additional shrinkage strain is actually caused because the coarse aggregate itself, or this coarse aggregate, it's not as stiff, and so the concrete is going to shrink more because it's not being restrained as much by the aggregate. So the contribution of shrinkage of the concrete, because of the shrinkage of the adhered mortar on that recycled aggregate, it's actually effectively none. And then looking at the mixes with the different water cement ratios, we end up seeing about the same trends. And yeah, so we're seeing about the same trends. As we use the recycled aggregate, this one's only 11% larger. This one here is 23% larger. Again, they are larger, so the recycled aggregate that came from San Diego still contributes additional shrinkage strain because of the adhered mortar. Again, the saturated one, 30%, and then 10%. So the aggregate that we allowed to, or kept from going through drying shrinkage before we used, really contributes more additional shrinkage to the concrete. And then again, the ones that dried out before we used them really did not contribute a whole lot of additional shrinkage because of the adhered mortar, even though the shrinkages were a lot larger. So these additional shrinkages, we're just attributing that straight back to the fact that the modulus elasticity of the aggregates were lower. It's not an additional shrinkage because of the adhered mortar. And so from the model, the mortar phases shrank more with the higher water cement ratio. And so these were the drying shrinkages that we got. No big surprise. As we go to higher water cement ratios, we did see that we get more drying shrinkage from the mortar phase. There's more water in the mix, so it goes through more drying shrinkage. And then sort of rearranging all those, this is the aggregates that were all allowed to pre-shrink, and yeah, so these were the ones that were saturated the entire time, and then these were the ones that were allowed to dry out first. Again, much higher additional amounts of shrinkage than the ones that were dried out beforehand. So that drying part does actually contribute quite a bit to reducing the amount of contributed shrinkage to the concrete. And then the high-quality recycled concrete aggregates from the supplier contributed more to concrete drying shrinkage than our younger lab-manufactured aggregates. So this is the results from the 3 batches made with the recycled aggregate that came from San Diego. 10, 20, 30% larger amounts of additional shrinkage, whereas the stuff that we manufactured and allowed to dry ourselves, somewhere between 3 and 15% additional drying shrinkage. This is the part that I'm still scratching my head over a little bit. Or maybe it's just this is how much we naturally expect to see. But like I said, I am sort of still scratching my head as to providing justification for this. I did point out we do know for this recycled aggregate, the adhered mortar is 34% of the aggregate. We don't know what it is for these 3. I sort of wish I did. Maybe a lot more of the mortar phase came off those aggregates than we are letting on. And so this brings up the final conclusions. The recycled concrete aggregate modulus elasticity plays a really significant role in countering the concrete shrinkage. It's measurable, and I think that actually has a bigger contribution as to why concrete with recycled concrete aggregates shrinks more. It's usually those aggregates have lower modulus elasticities, and so they're going to shrink more. And the greater the aggregate's modulus elasticity, the less overall shrinkage we're going to see. When recycled concrete aggregates are allowed to go through drying shrinkage, which is most cases in practice, prior to their use, the contribution of the overall concrete shrinkage is diminished. And then lastly, the recycled concrete aggregates contribution to overall concrete shrinkage is complex. There's more that needs to be done if we're really going to get into more complex modeling than I've done here. And really should be evaluated with the materials you're using before use if drying shrinkage is a big issue to you. And that's it. Thank you.
Thank you for a wonderful presentation. The question, when you did the shrinkage, because I saw two samples, two mixes have different shrinkages. Did you take the average of 3 prisms, or how did you do that?
I think it was the average of 2 prisms. As I'm trying to recall, yeah. But it was not 1 prism. It was at least 2, if not 3. Okay. But I think it was 2. And then so if you average the 4, maybe it will give you very close graph for the 2 mixes. Yeah, I mean, I don't like putting in averages because I mean, the data is what it is, and there's going to be a variation. Yes. But yeah.
And then the curing, when you did the shrinkage, what's the process? Did you put it 6 days in water and then started the shrinkage, or?
I'm trying to, again, that was one that I was scratching my head over just this morning. I was like, oh yeah, what was our process? Yeah. We do have a moist curing room, so it's in a moist curing room initially. And I can't remember if it was 7, 14, or 28 days that we did it first.
Could that make a difference on your final?
Yeah, we're following the ASTM on this, and I thought the ASTM was 14 days, but
Okay.
Yeah.
Thank you.
Yeah, thanks for the nice presentation. I saw your shrinkage measurement until 108 days or later stage. So after you put in the curing room and you took out like room condition. Okay.
Yeah. This went on for half a year. Student was anxious to graduate.
Okay. My question is something I'm thinking. People think about recycled concrete aggregates. Sometimes they're porous. Saturated aggregates may be used as an internal curing agent. So that looks like controversial to the testing result you have. So I'm thinking maybe people should rethink about recycled concrete aggregates because they're different than the other porous aggregates because they have mortar. So this saturated water maybe can make the mortar hydrate a little bit more. That looks like dry RCA can actually reduce the shrinkage, but saturated one and increase a little more the shrinkage.
Yeah. So I'm not quite 100% sure where the question is going, but and I think what you're addressing is that some of the thoughts with using recycled concrete is that it does have a higher absorption, and so you can really saturate them, get them filled up with 5% moisture, and that'll reduce the amount of like autogenous shrinkage because there's that additional moisture that's in it. And that's actually sort of where this research was going is that, I mean, actually part of our thought was that there might be enough moisture, it might actually reduce the amount of drying shrinkage we end up seeing because there's this additional moisture that keeps the concrete from shrinking. And that's, again, sort of where we're going. All I could say is that we're seeing this overall picture of this additional contribution. Before we mixed the concrete with these aggregates, we did saturate them, or at least they were in a pile with a sprinkler running over them. Sort of as standard practice. So they weren't dry when they went in, but that additional moisture can help reduce the amount of shrinkage. And so, there's a couple mechanisms that are tied in here, and that's why I'm saying this is still complex. We're just sort of lumping a couple of these mechanisms all into this one sort of factor that we're getting out of this. So, thank you. That was very astute.
Thanks very much for the very in-depth insight. I would have the following question. Like, normally a designer specifies basically a concrete strength and normally derives the Young's modulus from the strength, which is the normal pathway. Now, what you've shown is that basically the influence of the moisture content has a dramatic influence on the Young's modulus, if I understand that correctly from one of your slide, or perhaps I'm...
Say that again?
That the moisture content of the aggregates have, or the recycled aggregates have pronounced influence on the Young's modulus. Did I listen to that?
It wasn't the moisture content.
Or the drying condition? Or?
Well, that was something that was strange, and I don't have a right answer. And I think what you're saying is, yeah, so when we made our own aggregates, we processed them differently. Some were saturated and kept saturated, and then others were dried. Yeah, the ones that we dried out, they ended up coming out with really low modulus elasticities. I don't think it has to do with that drying process. I think something else happened during the manufacturing. So so I want to be clear that I don't think that having it dried out is creating such a dramatic influence on the modulus elasticity. I really don't feel comfortable making that as a conclusion. So
because that would have dramatic consequences actually in the design process.
Yes,
because we would now have to specify a minimum Young's modulus, which would then have consequences in the production process.
Yes.
Okay,
yeah. So
that doesn't hold.
Yes, I would not. No, please don't take that way as a conclusion. Please.
Okay.
Yeah.
Thanks very much.
Yeah.
Apologies if I missed this, but I was jotting a lot down. I don't even know if this is a solution, or I'm still trying to get my feet wet on shrinkage-reducing admixtures. Was that a consideration?
That's not what we're really driving at. Shrinkage-reducing admixtures could have an influence on it, but again, we're just coming back to, trying to understand the mechanisms. And, as one person pointed out, Barbara mentioned, the aggregates, have a higher moisture content. Maybe they reduce the amount of shrinkage. We're just trying to understand those mechanisms. Taking that other step, that might or that should help, but maybe it would be less in a case like this because of the way that shrinkage-reducing admixtures work. But it's
and I understand. Yeah, the mechanism is what you're getting at. I guess one more question would be sort of a solution. That and paste content. I don't know if you also could consider lowering the paste 20% or something lower than that to just resolve the issue. I know you're looking for the mechanism, but I'm just solution in my head as well. Just trying to see if that's an option if and when we come across a concrete like this.
Reducing paste content, reducing the water content in your mix, which comes along with the paste content. Absolutely, those are all the appropriate measures to reduce drawing shrinkage. Absolutely.
Sure. All right, thank you.